Hey guys, I'm Eli Burton.
And I'm Anuarbek.
And welcome to the first episode of the World of Engineering interview series. We will be bringing experts from around the world from different disciplines in the world of engineering to bring you the latest and greatest coming out of their industry. So today I would like to welcome our first interview guest to the stage, Vivas Kumar.
Yeah, thanks for having me, guys. It's great to be here.
Vivas, welcome. And we've known you for a long time. We're super excited to have you here to talk about battery technology and why the EV industry is going to LFP. But before we do that, tell our audience a bit about your background, where you came from, and what you're working on now.
Well, let me tell you guys actually a story, which is if you can see the background of Eli's image, when I met Eli for the first time, it was when the three of us were on the Formula One racetrack in Austin, Texas. And Eli was really kind and gave me his comic book, the Starman comic book, as a gift for coming out there. And I was moving houses recently, and I found it again because I've been preserving it. I have not even unsealed it. I've just been keeping it because I know that I'll be able to use it, in the future for something amazing. And this is one of those things that's going to be, worth millions of dollars one day, probably more than the equity of companies that I could be involved in one day. That one comic book from Eli.
You're too kind, my friend.
So, look, it's nice to see everybody over here, and thanks for taking the time to have me on as your first podcast episode. My background is that I'm an engineer by training. I've been in the battery industry for nearly a decade at this point. My initial claim to fame in batteries was that I was one of the senior managers for battery materials at Tesla. And Tesla was going through a very formative time when I was there. When I first joined, the Tesla Model 3 had just been announced and wasn't even in production yet. And I remember when I first joined the company, there were a lot of people in the world where I would mention the name Tesla and they would ask me, oh, what's that? Like the consciousness around electric vehicles was still growing. It was a relatively new concept. Governments were just starting to announce their plans for having the phase out of internal combustion engines. And most of the world still saw this company as being this small Silicon Valley startup that was doing something interesting and far off, but not something that was going to be, anywhere world changing by any means. And in the time that I was over there, by the time I left, Tesla Model 3 was out in full force, became the number one selling car in the entire world. The Shanghai Gigafactory was built, probably the fastest an automotive factory has ever been built ever. And, Tesla, just a few months after that, became worth nearly $1 trillion as a company. So I have seen with my own eyes, and I've been involved in an experience of taking a tremendous world-changing technology and playing a very small part in bringing that out to the world in full force in a very transformative way. And the lesson that I took from that time is technology is a tremendous force for good, and lithium-ion batteries as a technology for alleviating climate change, for electrifying transportation, is something that needs to be brought out to the prime time even more so that more and more segments of the world can get the enjoyment and satisfaction of driving an electric vehicle that all three of us on this call or on this podcast do. So inspired by watching Elon build the company, inspired by being part of it, I decided to found a company of my own in the battery supply chain, and the company is called Mitra Chem. So Mitra Chem, I founded with my two co-founders, Chiru, who's our CTO, and Professor Will Chu from Stanford University. And the thesis of the company is to go and accomplish three goals. The first is speed, to use an in-house machine learning advantage to significantly reduce the time to bring a battery materials product from lab to market. The second is a focus on iron-rich battery materials, which are safer, cheaper, and come from cleaner supply chains than your traditional Western nickel-rich solutions. And finally, it's building manufacturing scale with partners so that our products can be Inflation Reduction Act compliant and reduce the over-reliance that the Western battery supply chain has on assets that are geographically concentrated in China today.
What a great way of putting that. Thank you, Vivas. So now that we understand where you're coming from, what you're working on, let's jump into the focus of today's conversation. And that is why the EV industry is moving toward iron-rich cathode. What's the story there?
It's important to note that there's two major product categories of cathodes, but let's take a step back. So what even is a cathode? So inside a battery, you've got a cathode and you've got an anode. One's the plus, one's the minus. And a very simplistic explanation of how a battery works is a lithium atom in the cathode ionizes, and the release of electrons and the flow of electrons is the discharge of electricity from the battery. Now, cathodes are the most expensive part of lithium-ion batteries. They're also the part that determines the performance of the entire battery according to metrics like cost, energy density, cycle life, and safety. So cost is self-explanatory. Energy density, a very simplistic explanation is, how far can you drive on a single charge? You have more energy density, you've got more range. Cycle life is, how long will your battery live? Safety is very self-explanatory, right? Like, how do you reduce the probability of a thermal runaway event, of a fire event from happening? So there were two types of major cathodes being used in electric vehicles. One is iron-rich, and one is nickel-rich. So nickel-rich was the Western standard. If you look at your original Tesla Model S and Model X, or if you look at vehicles from GM, from Ford, from VW that were industrialized in the Western world, they preferred nickel-rich because nickel-rich has higher energy density. However, in China, vehicles tended to go more towards iron-rich because although they were lower energy density, they were also lower cost. And the Chinese consumer cared about cost. What's been happening in Western electrification is more and more of the products are being sold within the mass market units now, or more and more units are being sold within the mass market customer segments. So your vehicles that cost $35,000 to $45,000, but also outside of automotive, you've got more and more battery products being used in grid scale energy storage, where cost is the number one determinant of success. Because there's such a significant emphasis on cost, and customers are willing to sacrifice a little bit of energy density in order to get better cost, there's a general shift happening towards iron-rich cathode chemistries in the Western world. So then that begs the question of what are the products that matter within the iron-rich category? And those are the three products that we're designing. The first is LFP, lithium iron phosphate, a well-known, well-understood battery chemistry that's been used for over 20 years in automotive products in China and is increasingly becoming the product of choice for automotive products in the West as well, for mass market and medium-duty trucking. The second product is LMFP, lithium manganese iron phosphate. And this is a cathode chemistry that has a 10 to 15% energy density improvement against LFP. So what does that translate to is more range. And if you can find a cathode chemistry that has lower cost than nickel-rich, but still makes up for some of the range differential, that's a product that a lot of mass market consumers in the United States and in Europe would love to use. So that's where LMFP comes to play.
So quick question before we go into the next technology. Where do you see the LFP versus the LMFP differentiating in different products? Like, can you give some product examples of how you see those two being used differently in the consumer and in the storage space as time goes on?
Sure thing. The target market that we have for LFP is in the cheapest segments of mass market automotive and in grid scale energy storage, where cost is the number one determinant for any purchasing.
So we're talking products like maybe Tesla's next gen vehicle, like Model 3, Model Y type price point vehicles, home power wall, Megapack, those sort of products.
Robotaxi. Yep. I think the next phase, basically, yeah.
Let me get to Robotaxi, because LMFP as a product is preferred by medium duty trucking customers. And why do they like it? It's because they run vehicles on fixed routes that are highly predictable. And every single minute that they spend on the road is incremental revenue for them. And when they make purchasing decisions, they don't make purchasing decisions based on the cost of the material. They make purchasing decisions based on the total cost of ownership of the vehicle. So what that also means is if you put yourself in the shoes of somebody who's designing a robotaxi, the application is really not that different than medium duty trucking. You run relatively fixed, relatively predictable routes, especially within dense urban environments, and you care about the total cost of ownership of that vehicle over the lifetime of the vehicle. And every minute that that vehicle is filled, either with cargo or with people, and is running on those routes is incremental revenue to the company. So somebody like a robotaxi is probably likely to think about an LMFP. And without revealing too much, I will say that we've had conversations with customers about their designing vehicles for full autonomy and the battery pack that can enable that application to happen. And generally, they also tend towards something like LMFP as being the solution that they like. But if you ask everybody, what is your dream cathode chemistry? They tell you that they want two things. They want the performance of nickel rich with the cost of iron rich, right? Everybody wants it all. And that's where our final product, which is still at the R&D stage, gets to. So it's a product called LMX, and we're aiming to accomplish pack level energy density competitiveness against nickel rich cathode with an iron rich base.
Is it, Vivas, is it true that, like, I mean, I'm assuming when you were there in the early days with Elon talking about all the different segments that Tesla's going to make, the Cybertruck pickup, the robotaxi, the mass production vehicle, the Model S and X luxury sedans, there's a different, I mean, each of those car segments has a different like use case or whatever, right? For Cybertruck, it'll be like heavy duty pulling, like a work, that could be a different chemistry, battery chemistry compared to a Model 3 or Model Y. So in the future, are all these different cars, does somebody like Tesla or you guys helping Mitra Chem have different solutions for different segments?
This is a great question, and that's exactly where we're going to go. There's a imperception or misperception in the market that there's going to be one battery chemistry that wins everything. And I think the opposite is true. If you look at the segments that are electrifying, every single one of those applications has specific criteria for performance that are differentiated against each other. What the customer of a mass market vehicle cares about versus what a customer of a premium vehicle, a performance vehicle cares about are two very different things.
You know, in analog to the internal combustion engine, right? It's whether you've got a supercharged V8 Hemi or whether you've got a four-cylinder, the batteries are kind of the equivalent to that in this next generation of vehicles. Is that correct?
Exactly. So it's the entire drivetrain, right? It's the batteries, the pack level engineering and architecture, the battery management software, and the electric motors. That entire whole system approach is going to be differentiated by application. Now, your immediate next question is going to be, well, I see that, you've got like VW has announced an MEB platform, right? GM has announced an Ultium platform. Elon has talked on earnings calls about how he wants to take a platform approach to next generation vehicles. If everybody's moving towards these platforms where they're trying to unify the battery pack and the battery cell engineering to reduce their R&D and differentiation costs and just overall bring their margins up for their products, how does that comport with what I'm saying? So how that comports with what I'm saying is you're not going to have a different battery chemistry for every type of vehicle within a portfolio, right? You're going to have 3 or 4 battery chemistries that win 95% market share in automotive. It's just that when applications like mass market vehicles or medium duty trucking are picking their ideal battery chemistry, they're picking from those 3 or 4 options, whatever gets them closest to their performance criteria. Now, there's a lot more flexibility in battery management software. And of course, the buyer who buys these products is not just buying them for the batteries. They're buying them for a full product approach in solving the specific problem that they have. Aesthetics obviously play a role in this. Autopilot plays a role in this. The internal architecture, the service model, like there's a whole life cycle that the automotive company is selling you. But this specific decision around what is the best battery chemistry that enables the best bang for buck on the battery within that application is something that's on the minds of every single person doing supply chain or engineering in an automotive, because battery is the biggest cost driver for making a vehicle.
So 10 years from now, what do you think is going to be the dominant battery technology, both in the West and then also in China?
Everyone is shifting towards iron rich. And when we saw at Mitra Chem that this shift was happening, that's the reason why we doubled down on iron rich. It was a very contrarian bet when we started this company in early 2021, when nickel rich was still the Western king, to go towards iron rich. But now here we are, almost 3.5 years after the company was founded. And you've got every single major battery cell maker selling into Western markets, announcing plans to go towards LFP. Every single automotive at scale in the Western world saying that they want to integrate more LFP into their architecture for mass market EVs. And as that share of iron rich grows, and as that volume grows, the manufacturing cost and the proliferation of the manufacturing footprint for the iron rich is also going to grow in the Western world, giving it more and more of an advantage against nickel rich. So what also disadvantages nickel rich is the supply chain for nickel and cobalt is highly constrained. Getting primary materials from mining and dealing with the velocity of changes of the price on the London Metal Exchange is very difficult for people who are sourcing these materials. I know because I used to be one of these people. I used to source these materials when I was a buyer at Tesla. I worked with an amazing team, and we all sourced nickel, cobalt, lithium, aluminum. We also thought about sourcing phosphate for LFP, and consistently far and away, the nickel and cobalt supply chain was such a huge thorn on the side because there's so little you can do to control the long-term pricing action over here that, of course, for somebody who wants reduced pricing volatility and more certainty of supply, they're going to shift towards iron rich. So the irony is the differentiation was iron rich went to China, nickel rich went to the West, but here we have the technology from China coming and eating share in the West in this market.
So speaking of Mitra Chem, and you said you guys have been working on things now for a few years. We've got a clip actually from a couple of years back we're going to share here real quick, and you can let us know how progress is going on some of these technologies.
Finally, hold me accountable. 2 years from now, I'm going to come back to Stanford Energy Seminar. I'm going to put this slide back up, and I'm going to tell you what we did to make LFP go up to the sweet spot and how we're thinking about going to quadrant number 1, which is the holy grail of cathodes. High energy density at the lowest cost possible. Hold me accountable. With that, I'd like to say thank you. I will open up the floor for any questions.
All right, we're here to hold you accountable. How goes progress?
You can tell from my mask that that speech happened still during COVID pandemic. And actually, this company was started during the COVID pandemic as well. So, one good thing to come out of that crazy time in our lives was I had all this time in my hands, so I figured I might as well start a company, right? So hold me accountable. We did make LFP at multi-ton scale, and we are sending out these samples to customers now. But in our progress towards the sweet spot, our progress on LMFP and LMX speaks for itself. So on LMFP, we have a great strategic partner, Saint-Gobain Ceramics, that we work with. And the product is going through multiple different stages of validation before we do some rigorous customer sampling activity. But that LMX product that I described earlier on this podcast is the product that can sit in that sweet spot. And in the 2 years since that speech, we have lab scale validation of a product formula with a synthesis process that could scale. So what do I mean when I say those words? When you make something in a lab, it doesn't necessarily mean it's going to be manufacturing ready. And decisions that you make in the lab need to be geared towards manufacturing readiness for you to be a commercial ready product. What are the two constraining variables we use in our product development process? The first is synthesis methodology has to be mirrored with at-scale equipment that already exists in the world. So minimize customization of your chemical process flow sheet as much as possible. The second is use materials with existing at-scale supply chains so that we don't have to go out and build an entire new supply industry in addition to building our own products. So we've used those two constraining factors to design our LMX product. And our LMX product is ready to go at the lab scale. We've decided to focus our efforts mostly on LFP and LMFP in the short term, rather than continuing to take LMX to pilot scale. Because today, so we're recording this podcast in May of 2024, the customer push is towards more LFP, primarily first, because cost is making so much of the purchasing decision for these automotives. We live in a time of high interest rates, in a time where battery costs need to be slashed to keep pace with how much automotive margins are being crushed. And so the same customers that last year were talking to us about how do we bring LMX to the world are now talking to us about how can we get LFP ASAP. And then right after that, how can we get LMFP? So we're focusing most of our efforts on those two products first, knowing that we can turn back on the LMX work to go from research scale to pilot scale when the market is more ready and willing to accept that product.
So you talked about you guys have sent samples back to customers on a number of different products. And I've seen on your guys' website, that's a core part of a lot of press releases that you're now delivering samples to customers. For people who aren't familiar with battery technology development and battery supply chain, what goes into what all has to happen before you're sending those samples to customers? And why is that such a significant milestone?
It's a significant milestone because customers have a limited number of samples that they can test, because their engineering teams and resources are not going to take every single thing that comes to them. And if you put yourself in the shoes of a large automotive or battery cell manufacturer, they're being approached by potential customers, potential suppliers all the time. So the first step is getting the customer comfortable that you're a credible counterparty who actually knows what you're talking about. The second step then is showing them the promise of a fruitful relationship, not only with today's products, but also that you have a roadmap to get to future products that matter for them. The third step then is to send them a sample and have it pass against their rigorous testing standards before you can then do subsequently larger and larger samples for more and more representing manufacturing process flow lines. So even getting to the stage where somebody takes your sample, runs it through their rigorous testing, invests their engineering resources to do so, and then tells you this is passed and we actually want to keep investing our time and resources into testing more and more materials. That's a big step for any automotive or battery cell player to take on.
Very cool. Just to kind of shift a little bit, from what I'm understanding, this almost sounds like when people ask me about Tesla, I tell them it's a hard company to keep up with because of the pace of innovation. This is same with Mitra Chem, that like the continual, like you're able to quickly, you said cut down the R&D stuff by 90%. So you guys are iterating so quickly. It's hard to basically keep up from a research standpoint, I guess, or implementation even.
If all we're doing is making the best powder, then somebody else will copy it.
Right. And I guess there's
so the question for us that we were trying to solve, Anuarbek, just cutting straight to the chase, because the point you're making, anybody who's out here, if this is the one thing you learned from this podcast, right? Anuarbek's question got right to the point. Pace of innovation is what determines winners in highly technical and complex industries. If all you're doing is making the best product, somebody will copy it. You will go obsolete. They who copy it will likely do it at a lower cost over time, especially if you're a Western player, you're trying to manufacture at scale. An Asian player will manufacture it at lower cost and at bigger scale than you. The only way you win is by the time they copy, you've come up with an even better product.
So let's talk about that, because I think we are starting to see Tesla was first out of the gate by kind of a long shot in the West in EVs and developing technology. China is now starting to catch up, and we're starting to see China using body types, gigacasting, taking the same approaches that Tesla has. How do you see that race in automotive, that technology, the later adoption, affecting the competition between Western auto and Chinese automakers in the near term?
The biggest story in automotive right now is Chinese autos. And I hope that every single person here get an opportunity. Go look at the photos of the vehicles from the Beijing Auto Show. Like, these vehicles are amazing. Chinese companies are not simply just copying American automotive concepts anymore. They're coming up with even better automotive concepts that they're exporting out to the world. I mean, they've become one of the largest exporters of vehicles worldwide. So why is this important? And I just want to say, like, Mitra Chem is an American company, and I'm very proudly American, but I've also spent a lot of time in China doing business, especially as it relates to my prior career at Tesla, but also even today, the best battery materials companies in the world are in China. And my approach very much is you want to learn from the best so that you can also become the best one day. And the observations that I have from doing business in China is there was a bet made very early that the leapfrogging that China could do in the global economy was to build a domestic electric vehicle manufacturing footprint when EVs were still a relatively new concept in the mid-2000s. And because they have 15 years of compounding advantage from learning manufacturing at scale, they know that they can bring their costs down lower than anybody else, but they're now willing to invest the incremental margins that they make on new, better product development in a way that Western companies are hamstrung from doing so. So their products are better able to reach mass market faster, but also be more appealing to their customers in the end. And there's a real concern now in Europe, especially, that Chinese autos are just going to flood their market and outcompete the European automotive manufacturing base. It's not as true in the United States, right? Because the U.S. auto companies, and this goes beyond Tesla as well, GM and Ford and Chrysler and VW and BMW, they all have very significant brand recognition here in the United States, and their products have been purchased by customers who are relatively loyal to those brands for decades at this point. So it's not like there's going to be an immediate switchover. And also the US has instituted protective tariffs against this kind of flood of automotive products from China into the US. But going back to the ethos of wanting to learn from the best, there's a lot that's happening right now with product design and product development for automotive with the Chinese automotive companies that the US automotive companies can learn from as well.
So it's funny you mentioned the tariffs. Like 30 minutes ago, news just broke that the Biden administration is significantly increasing tariffs on Chinese automakers coming into the US because they have to keep Western auto competitive.
Yep. Yeah. And by the way, this isn't the first time that protective tariffs of this kind of been implemented, right? We've seen that across the commodities value chain for clean energy. The U.S. government is being very aggressive. So there's the Bipartisan Infrastructure Law and the Inflation Reduction Act. The confluence of policy, legislation, and funding that's happening to get clean energy solutions and technologies manufactured in the U.S. is at a level that we've never seen before. But in addition to that, protecting the domestic market from competition from abroad with protective tariffs started during the Trump administration in this industry and has only grown in prominence and ferocity under the current administration with Joe Biden.
You know what kind of thinking forward to the next 5-10 years, a lot of what we're about to go through, this shortage of raw materials for batteries, sounds a lot like what we just went through with the chip shortage. Can you speak to that? Is that a good analogy? Like, what's going to happen, if we are asleep at the wheel over the next decade and the EV demand goes through the roof and the supply chain isn't ready with the right materials and the right technology to basically be there for the supply for the demand? Can you speak to that?
What unites chips and batteries? They're both platform technologies. So a platform technology is a product upon which multiple other different products are built. So think about how many things in your life use chips. Think about how many are now using a portable power source that's chargeable and dischargeable, like a battery.
Everything.
Both of those technologies also have taken 80-year technology development cycles to get to where they are today. It's just that chips were more relevant for the information age, and because of a confluence of different factors, right, which we don't need to get into in this podcast, but by itself as an hour-long podcast, semiconductors saw huge investment from the United States during the Cold War. And then you had other national governments make huge bets around semiconductors as well. Namely places like Japan, Korea, Taiwan. And now semiconductor props up majority parts of the industry in those countries. So what did the United States do with batteries? Most battery research, especially the Nobel Prize winning work, was done as a result of Western academia and Western industrial research. But the shift towards the industrial supply base for this technology moving away from the United States and towards Japan, Korea, and China happened much faster because of consumer electronics revolution in the 1990s and 2000s and the electric vehicle revolution that's been happening in the 2010s and 2020s. So the way in which the United States does not squander the relative competitive advantage of its overall industrial footprint is by ensuring that pace of innovation remains high. There's a constant focus on decreasing the cost of manufacturing. And you can either do that through direct engineering efficiency gains by decreasing the input costs of supply chain, or by instituting protective tariffs to make everybody else uncompetitive. And actually, I will commend, purely from the standpoint of game theory, in understanding the interests and protection of those interests for the US industrial supply base, I will give credit to both political parties. Under a Republican presidency with Donald Trump, under a Democratic presidency with Joe Biden, both of them have been highly focused, using different tools in some cases, but have been highly focused on how do you protect the competitive advantage of platform technology industries in the United States so that we don't have to ever relive the deindustrialization that happened in the 1990s, 2000s, and 2010s. It's an important topic for us to discuss here on the World of Engineering podcast because when I was an engineering student, when I was 18 years old, right, I thought that just doing the problem sets well, being able to build, cool gadgets in my college classes would be enough to qualify me as being an engineer. But now that I'm a CEO of a multinational technical company, I'm seeing that geopolitics, economics have as much an impact on what technology actually comes out to market and not just engineering. Don't get me wrong, the baseline is still having great product, great engineering at a cost that's attainable to the customers that you're going for. But in terms of what technologies win over time, having a whole of industry approach and view that incorporates multiple of these viewpoints, which are reflected in the wonderful questions that you guys are asking also for this conversation. That's actually what defines what great engineering is.
Vivas, man, thank you so much for this. For people who want to follow what you're doing, please let them know where they can follow you. And also, if they're interested in learning more, maybe you can point us towards some resources for inspiring engineers out there who want to get into the field of batteries and help push this forward.
Sure. We're at mitrachem.com. I'm on LinkedIn as Vivas Kumar, Twitter at VivasVK7. And then if you want to learn a little bit more about batteries, just find some of my talks on YouTube, like the little clip that Eli showed over here as well. Because you can trace back the history of lithium-ion batteries to some of the speeches that I've been able to give on the topic.
Thank you so much, Vivas. We can't wait to have you back next time.
Thank you, guys.
Take care, man.